Welcome. This is Terry Fox. We're into section 5. This regards connectors, and we're talking about making SERDES circuits work. You can get more information on my website. This is probably one of the more difficult videos because there's so much to go through here. So take it for what it's worth, and here we go. The first thing is we've got to go back to the beginning of the right the first time method. What does it mean to have a right the first time method? Well, it means quite simply that the first time we build this thing, it works properly and we don't have any problems with it. It is fully operational. It's manufacturable. Everything works the way it's supposed to work. Now, in order to do that, you've got to use design elements that are predictable over the frequency range necessary. So if you happen to have a board layout or a bypass capacitor strategy or a power delivery system that works fine at 50 megahertz, realize that it may not be adequate for 150 megahertz. So just remember, you've got to look at these things and say, how do these design elements work as I go across the frequency range? Now, when I start looking at SERDES parts, realize that we're working up in the gigahertz range. These are microwave type things. So understand what the design elements are and that they are predictable over the frequency range necessary. The second thing is you need to know the signal that is going through that design element. What is the noise margin? Because if I add up all of the design elements, and if their additive degradation of the signal is within the noise design margin, then this thing will work. But please, when you add up these numbers, keep 3 dB in your pocket. I came from Hewlett-Packard back in the 70s, and I remember Bill Hewlett shaking the change in his pocket and talking to a group of young engineers and saying, at Hewlett-Packard we always keep 3 dB in our pocket. By the way, Hewlett-Packard now went to Agilent, now it's Keysight. Anyway, it was an awfully good company back in my formative years, and I learned some really excellent methodologies that have kept me safe over the years. So now let's get into connectors per se. When you look at a connector, the first question you've got to answer is, what type of signal am I dealing with? Am I dealing with an analog signal? Am I dealing with a digital signal? Am I dealing with a differential type signal? If it's differential, is it something with magnetics in it, like for example Ethernet 10 base T, or is it something that is more like an LVDS signal, which we would call a complementary signal ended? So the question is, what type of signal are we dealing with? And once you know that, I want to know, what is the noise margin? The noise margin of a single-ended signal is down around 2 dB. The noise margin of an LVDS type signal is probably 12 to 15 dB, possibly even more in certain cases. Now, as soon as we know what the noise margin is, and we know the type of signal, then you can start making assumptions about the return current. So please, if you're not sure about where that return current flows, or let's say the importance of where it flows, then go back and review the LVDS and true differential signal video, because this is critically important. You've got to understand where do the return currents flow, and I'm not trying to say that this is a perfect world where all of the return current flows one place or the other, but the biggest mistake that people make are to think that all of the return current on an LVDS signal flows on the other half. That is, the return current for the P flows on the N, the return current for the N flows on the P, and that is absolutely not true. So go back and look at that video to get that cleared up. Next thing you have to look at is the frequency range. What is the information band that connector has got to pass this information? And you've got to pass it both from an amplitude standpoint, which we would call attenuation, but you've also got to pass it from a linear phase shift standpoint that in the case of SERDES signals will end up looking like jitter. Now, when I look at the connector and I say, how does it work? The key thing here is, where is the return current? Where's the return current and where's the frequency range over which this thing will work without resonances? So resonances are a big deal. If you want to get a little bit more on that, go back and look at the via business. That is a very similar issue. Finally, I must have definitive data to prove that a particular connector works well within some well-defined parameters. Well, how do you get that definitive data? Well, one of the ways that you can do that is certain connectors are obvious. If I've got a coaxial SMA connector, I know that those things work up to about 18 gigahertz or better because that's what we've been using for microwave work for a long, long time. If it's a BNC connector, I would guess that that thing will probably work up to probably a gigahertz or above. Type F, those connectors are used in, you know, cable TV, etc. So anyway, if the connector is obvious, then that's a lot more safe choice than having pin grid arrays or edge card connectors where they are not obvious at all. Now, let me throw in one other thing in this type of connector. If you're using a Samtec or a Michter connector or something like that, where it's got a ground spade between the leads, those again are very good high frequency connectors. You can get excellent data on them, and it's very obvious that the return current is supposed to flow through that center spade. So hook it up correctly, make sure that you've got enough. If you've got something with a spade in it, then make sure that that spade is connected to ground on the solder connections through multiple vias. That spade is wide for a reason, and you have to connect it to the ground plane with many, many, many vias. Maybe not many, 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 but plenty of them. Okay? Now, if I've got an industry standard connection like the PCI Express, then I've got many examples of when this thing works. The problem that I find with PCI Express connections is that people look at the connectors and they assume that they understand how it works. Then they build a different type of board, and it is an expansion on this, and what they do is they expand outside of the range where this connector either works or the way the connector is implemented works. So please make sure that you understand how it works, why it works, what's the frequency range, etc. before you start relying on this type of thing. Finally, we've got manufacturer data. These are things like S parameters. Maybe it's real honest-to-goodness test data they got out of a vector network analyzer and de-embedded the S parameters. Might be graphs, etc. Finally, we can get down to 3D simulations, which are excellent as long as you've got the 3D simulator that will do this, and you've also got the skill to run that 3D simulator. And then finally, there's physical test data. If you don't know how something is going to work, it's a lot cheaper to build a test board and go test it than it is to build a complete design and then go check and chase the errors. Now, this is not a huge amount of data on connectors. This thing is much too complicated to put into a simple video. What I would advise is go get some professional help if you've got questions on the connectors, because if you can't come up with data that says there's some sort of obvious reason why I ought to believe this connector is adequate, if you don't believe that, if you don't have that data, if you don't know where the return current flows, then please do yourself a favor and go get the data before you commit your design to a particular method. So anyway, that's kind of the end of it for section 5 on connectors, and I wish you the best, and off we go.